Hello everyone. Today we are going to study the instruction set of 8086/8088 microprocessor. Earlier in a topic on how 8088 works, functioning and working mechanism of 8088 microprocessor was discussed, and later in a topic on instruction set part 1, we discussed the data transfer and add instructions and its variants. As we have studied earlier that the instruction set of a microprocessor defines the basic operation that a programmer can use and design programs using these instructions. The 8086 microprocessor provides powerful instruction set containing 117 basic instructions. The basic instruction has a wide range of operands and addressing modes available, so that the basic instruction expands into many more instructions executable at a machine level. We divide the instruction set of 8086 in 5 different categories. First is data transfer instruction, second is arithmetic instruction, third is logic instruction, fourth is shift instruction, and fifth is rotate instruction. The first group of data transfer instructions as well as one of the arithmetic instruction add and its variants were discussed in the previous topic. Today we are going to discuss another arithmetic instruction called sub, used for subtraction of one number from another. The instruction set of 8086 microprocessor provides an extensive set of instructions for implementing subtraction. The format of the subtraction is sub D, S, where D and S are two registers which you can specify with the sub instruction, and it performs a subtraction operation as D, which is the first register, equal to D minus S. That means, the contents of second register specified with this sub are subtracted from the first register, and the result is finally stored in the first register designated as D here. A variant of sub is SBB, which stands for subtract with borrow. Abbreviated in short, the instruction is SBB. The instruction is similar to sub. The only difference is it also subtracts the contents of the carry flag from the destination, which is just designated as D. That is, the result of SBB instruction SBB D, S is D equal to D minus S minus carry. Assume if the contents of register AX and CX are 1, 2, 3, 4 and 0, 1, 2, 3 hex respectively, and the carry flag is 1, then the result of SBB AX, CX will be AX equal to AX minus CF. The value thus stored in the AX after the execution of SBB instruction will be 1110 hex. Another instruction negate, abbreviated as NEG, performs on data operands. The format of NEG instruction is NEG operand. If, for example, if the instruction is negate BX, the computation performed will be 0 minus BX. That means, 0 and minus BX is replaced by 2's complement of BX. That means, complement all the bits of BX, add 1 to it, and that is the result of negate BX instruction. Take an example. Assume the value of Bx is 002 Ch. Then after the execution of NEG Bx instruction, the result FFD4 hex will be stored in the register Bx. In the earlier topic, the addition of BCD and ASCII numbers was explained using DAA and AAS instructions. The sub U and SBB instructions can also perform subtraction on numbers represented in these formats. However, to bring the result in BCD and ASCII format, the adjustment in the result is needed. In case of ASCII subtraction, the instruction ASCII adjust for subtraction. In short, AAS instruction is useful. In case of packed BCD arithmetic, the instruction decimal adjust for subtract, which is DAS, adjusts the result obtained after subtraction of two numbers through the instruction SUB or SBB. Take the example of an instruction sequence sub AL comma BL and then followed by the subtraction we write AAS. Assume the value of AL 09 is stored in the ASCII format as 39 hex and value of BL contains 04 stored in the ASCII format as 34. After the execution of the sub and AS instruction, the result is 35 hex with AH unchanged, as the subtraction does not result in a borrow. In case of a BL containing 39H and AL contains 34H, the result is 35 hex in AL and AH value is decremented by 1 because of the borrow generated out of subtraction, as 34 hex is less than 39 hex. The next instruction in the category of arithmetic instructions are the operations are available on numbers represented in binary, BCD as well as ASCII formats. The instruction MUL processes multiplication on two unsigned binary numbers. The format of the instruction is MUL 8-bit operand or 16-bit operand. For example, the instruction MUL-CL when executed does the multiplication of CL with another 8-bit register AL. As in the multiplication, it is assumed that AL is going to be one of the operands taking part in the multiplication and another operand you specify with the instruction. AL is mandatory as one of the operands in 8-bit multiplication. The result so obtained is stored in a 16-bit register AX. On the other hand, if the operand specified with the mul is a 16-bit register say CX, the multiplication performed is AX and then is multiplied with CX, and since the operands are two 16-bit numbers, the result of the multiplication can be at most 32 bits and therefore, the result is stored in a 32-bit register pair DX, AX. It specifies that the 16 most significant bits of the result are stored in DX and the 16 least significant bits of the result are stored in AX. For the division operation, div instruction is used, which is the next instruction like mul instruction. The format of the div instruction is div 8-bit operand. Again, you only need to specify a single operand with the div instruction. For example, div CL results in the division of the register AX by CL, and when the CL is divided by the register AX, the result is stored in the register AL, which is a quotient. 8-bit result is stored in the register AL and the remainder is stored in the 8-bit register called AH. Another example of div, which is the variant of div instruction, is div CX, and that results in the division of a 32-bit number expressed as a pair DX, AX by the register CX. The result quotient is stored in the 16-bit register AX and the remainder is stored in another 16-bit register called DX. The variant of the instructions as explained before mul or div is imul and idiv instructions respectively. The instruction assumes the number is represented in signed format and produces the result again in the signed format. Consider two numbers FE H represented in hex format as the hex number FE and another number FD again represented in the hex format as FD, are stored in the register say AL and CL. The result of instruction mul CL will be FD02H, FD02 hex. That means, if the multiplication is unsigned, the result will be FD02H, whereas in the instruction IMUL interprets the numbers in the signed format as -2 and -3. The integer multiplication generates a result -2 multiplied by -3 and the result is equal to 0.6 instead of FD02 if it is an unsigned multiplication. So, a result 0.6 is stored in the register AX after the execution of the instruction IMUL. All the flags are affected similar to the flags affected for other arithmetic operations as explained before. The instruction IDIV considers the number in the signed format and accordingly generates result also in the signed format. The division of one negative number with another negative number generates a positive result. The result is negative if one of the numerator or denominator in the division instruction is negative. The multiplication and division operations can be performed when the numbers are represented in packed BCD format. Assuming the two numbers whether 8 bits or 16 bits are represented in the packed BCD format. When these two numbers are multiplied or divided using mul or div instruction, the adjust instruction for multiply and the adjust instruction for division transforms the result back in the BCD format. Next, we discuss the logic instructions of 8086. The 8086 microprocessor has instructions for performing logical operations like AND, OR, exclusive OR and NOT operations. These operations are performed bitwise between the pair of specified operands. For example, the instruction AND AX, CX causes the contents of AX to be ANDed with CX. The result is stored in the register AX. The AND operation is typically used to check the status of a particular bit or set of bits. If we want to check whether the fifth bit from the right of the register AX is 1 or 0, then instruction AND AX, 10H will result in a non-zero value if the fifth bit is 1, else the result will be 0. Accordingly, the status of 0 flag will be set to 1 if the result is 0. Take another example of AND operation related to divisibility check. The characteristics of a number divisible by 8 are that it contains zeros in its last 3 least significant bits. For example, 8 is represented in binary format as number 1 followed by 000. The number 16 is represented in binary format as 1 followed by 4 zeros. The number 32 is expressed in the binary as 0100 followed by 000, and if the given number is ended with the number 07 hex and the result of the operation is 0, then we can conclude that the number is divisible by 8 as its last 3 least significant bits are 0. Similarly, the OR operation performs bitwise OR operation between bits of the specified operands. Both 8-bit as well as 16-bit OR operations are permitted. Assume the following instruction sequence: move AL, 01010101 binary, followed by the second instruction is OR AL, 10101010 binary. The first instruction initializes the register with the value of binary as 01010101 binary and then executes OR operation with 10101010 binary. The result of the OR operation is stored in the AL as 1 1 1 1 1 1 1 1, all ones in the 8 bits. The next instruction is the exclusive OR instruction. The exclusive OR instruction performs bit-wise exclusive OR operation between the specified pair of operands. Again, the 8-bit as well as 16-bit exclusive OR operations are permitted. To explain an exclusive OR instruction, assume the following instruction sequence. Let us say you initialize the register AL with the help of move instruction. You specify move AL comma 01 01 01 01 binary, and then you perform the exclusive OR operation of register AL with 10 10 10 10 binary. The first instruction initializes the register AL with the binary sequence as displayed on the screen 01 01 01 01 B, and then executes the exclusive OR operation with 10 10 10 10 binary. The result of the exclusive OR operation is stored in the AL as shown. The next instruction is the NOT logical operation. The NOT logical operation requires a single operand, unlike AND, OR and exclusive OR requiring 2 operands. The instruction NOT L complements or inverts each of the bits of the specified operand. For example, assume the following instruction sequence, which is move AL comma, initialize the register AL with a specified binary value, and then we execute the instruction negate AL, neg AL. The first instruction initializes the register AL with the contents as shown, and then when the instruction neg AL is executed, it complements all the bits of the register AL, and the final result as shown. As you can see that all the bits of register AL are complemented. That means, if earlier the bit contains 1, now it contains 0. If the earlier bit contains 0, now it contains 1. The next category of logical instruction is shift and rotate instructions. The shift instructions of 8088 can perform 2 basic types of shift operations. They are called logical shift and the arithmetic shift operations. Also, these operations can be performed to the right or left side. The shift instructions are shift logical left SHL, shift arithmetic left SAL, shift logical right SHR, and shift arithmetic right SAR. Assume the following instruction sequence. Again, we initialize the contents of the register AL as shown below, and on this register AL containing 8-bit binary value, when we apply the instruction SHL AL, the instruction SHL AL comma 1 shifts the contents of register AL 1 bit left by 1. The result of the most significant bit is copied to the carry flag, and the least significant bit is filled with 0. After the execution of SHL AL comma 1, the new value of AL will be as shown below. Also, the old value is shown. So, you can see the effect of shift left operation on the register AL. The shift left operation can be used for efficient multiplication by the power of 2. A shift left by 1 results in multiplication of the number stored in AL by 2. As you can see, if the original value of the register AL is 4, now it becomes 8. A shift left by 2 bits results in the multiplication by a number 4 and so on. The number of shift operations can also be specified in the CL register with the instruction SHL AL comma CL. The number of shift instructions are software controlled. The number of shifts can be specified in the CL register before the execution of the shift instruction. The instruction SHR AL, 1 shift the contents of register AL by 1 bit in the right. The most significant bit is filled with 0 and the least significant bits are copied to the carry flag. The shift right can be used for efficiently dividing a number by the power of 2. Another type of shift is shift arithmetic. In the arithmetic shift to the left, the SAL operation, the vacated bits at the right of the operand are filled with zeros, whereas in the arithmetic shift to the right, the vacated bits on the left are filled with the value of the original most significant bit of the operand. Thus, in the arithmetic shift to the right, the original sign of the number is extended. This operation is equivalent to division by powers of 2 as long as bits shifted out of LSB are zeros. The another set of instruction is rotate instruction. The rotate instructions are similar to shift instructions. The rotate instruction causes the contents of the least significant bit to be reloaded to the most significant bit in case of the rotate right operation. Similarly, the rotate left operation, the most significant bit is copied to the least significant bit. A variant of the rotate left or rotate right is through the carry flag. In case of the rotate left with carry flag, the carry flag participates in the rotation in the sense that most significant bit is copied to the carry flag and then the carry flag is copied to the least significant bit. Again, the rotate operation can be done multiple times as specified in the register by the following instruction. You can write RCR BX, CL. That means, if the CL contains a value 3, the rotate operation is performed 3 times. The instruction rotate right with carry performs the rotate right operation a number of times as specified in the register CL as explained in the example. So, what we have learned today are the various instructions of 8086, how they are executed, the instructions related to subtraction, multiplication, division and its variants were discussed. The logical instructions like AND, OR, NOT and exclusive OR were discussed. The shift, rotate and its variants were explained in the end. Thank you.